Hello, my name is Jackeline Rizo, and I'm a mechanical engineer major at UC Merced. This summer, I had the opportunity to conduct research at the WSU IREX under Dr. Matthew Whitenane's lab, where I focused on a novel mechanical cherry harvesting, specifically a shake and catch harvesting system designed to improve efficiency in cherry picking. Washington is a powerhouse in the sweet cherry industry, producing around 60% of the nation's supply. That's about $400 to $500 million in annual value. What makes this even more impressive is that all of these cherries are harvested by hand. This creates a huge demand for labor, and unfortunately, that labor is increasingly hard to find. With agriculture labor shortages on the rise, it's clear that growers need more automated solutions, ones that can reduce costs while keeping up with the harvesting demands. My project was driven by this exact issue. We want to reduce harvest costs and improve efficiency. But here's the catch. We also want solutions that aren't overly dependent on the tree size or orchard layout. So I focused on one specific method, mechanical shaking. Specifically, I studied on how different durations and frequencies of a shaking can impact fruit removal. The idea is to find a combination that works effectively while being able to adapt. Previous studies tells us a few key things. First, successful fruit removal depends on both how strong the fruit is attached and how much energy the shaker delivers. Second, there isn't a one size fits all solution. Shaking needs to be customized based on the fruit type, its ripeness, and even the structure of the tree. High frequency, short duration shaking can work really well, but only if it's tuned properly. The problem here is that not many studies look at how duration and frequency interact, especially for cherries. Most studies just test one machine design or one shaking setting. This is how a UFO block looks like. The shaping and how the branch look. This is important to see and understand because you can visualize the difference between the branches in the UFO system. The UFO system's here and its branches are here. And you can see the difference in this UFO system in comparison to a very traditional orchard, having the branches a little bit harder, like you can see here to insert this mechanical cherry picker that we'll see later on. My goal was to test the effects of both shaky time and its frequency on a cherry removal in two cultivars, Skeena and Sela. These two respond differently to mechanical stress, so comparing them gives us more insight. We did our testing in the Rosa block of the UFO orchard. We used 40 branches total. Each one was shaken at either low or high frequency across 4 time intervals 1, 2, 5, and 10 seconds. That's 5 branches per setting. We used a mechanical shaker and a catchy frame to collect the cherries, digital calipers to measure the branch thickness, and a digital force gauge to measure how strongly the cherries were attached, called a pedestal fruit retention force, or PFRF, which is what we referred it to. We also counted the fruit before and after each shake to calculate the removal rates. These next two slides are going to show the actual setup in action, how the shaker looks, which we can see right here, the mechanical cherry picker, how it looks. And this is the caliber that to measure the diameter, the digital force gauge right here. This is the catching frame. And this is another possible mechanical cherry picker, but we did not focus on that one. Seeing this helps visualize and scale of the work in progress. This shows the location. This is the UFO block we used. And this is the section that we focused on right here. This middle section, we focused on the section throughout the whole entire trials. So this didn't change. The section was the exact same in every single one. This is a little bit more close up so you could see it. This is an example of the high and low frequency that was used. They're in slow-mo because it's a little bit easier to visualize how many thrusts are per second. Let's look at Sela first. Its average fruit retention force was about 219 grams. Sela performed better at a high frequency, especially at 10-second mark, removing around 50% of cherries versus only 20% at the low frequency. A really interesting result was at 1 second, high frequency removal was 36.9%, while the low frequency removed only 4.6%. This shows that even very short bursts can be very effective if its frequency is high enough. Now for Skeena. Skeena had a higher average fruit retention force of 409 grams, so it was harder to detach. Still, Skeena respond really well to high frequency shaking. Even at just 2 seconds, right here, we got over 35% removal, and at 10 seconds, we hit nearly 80%. Low frequency was much more less effective, only 8% at 1 second and 50% at best. This shows that Skeena needs both longer and higher frequency shakes to get good results. So what does this mean? Skeena was clearly more sensitive to frequency. High frequency made a huge difference, with removal rates jumping drastically. Sela, on the other hand, had more consistent results between low and high frequencies, but high frequency still offered a more stable removal rate. It's also important to know that Sela had a much lower PFRF, meaning its fruit was easier to detach overall. Now we're looking at the caliber, which is the diameter on the tree trunk, and how this affected the removal. This mattered much more in Skeena. Larger tree trunks in Skeena cherries were harder to remove, which matters for designing harvesting machines. Sela didn't show that same trend, suggesting that the fruit size on that diameter isn't as important for removing the cultivar. This is a visual example of how 12 millimeters diameter looks in comparison to 26. When we compare low versus high frequency directly, we see that both cultivars had the biggest difference at just 1 second. Skeena showed the most dramatic frequency effect, while Sela was less impacted. Again, this supports the idea that frequency is a much bigger deal in Skeena. To summarize, Skeena performs best with short, high frequency shakes. Frequency plays a major role in the remover. For Sela, it's more stable and less affected by frequency or its fruit size diameter. For both cultivars, 1 second low frequency shakes were almost useless. The main takeaway is that different cherry cultivars need customized mechanical shaking settings. There's no universal solution. Each one has a unique harvesting profile. In conclusion, this research shows that mechanical shaking can be optimized based on the cherry variety. This has real potential to make a harvesting more efficient and reduce the need for manual labor, which is especially important given the ongoing labor shortage in agriculture. I'd like to thank Dr. Matthew Whitening, my mentor, along with Gabby, the entire Whitening Lab, and the teams at WSU IREX Center and the Ag Aid for their support and guidance throughout this project. Thank you.